So in the last class, we were talking about how to recover residual waste heat energy. Okay, that was the topic: waste heat energy or residual energy. In essence, you have very low enthalpy, either gas, temperature, uh, low temperature, either gas, exhaust gas, for example, from a combustion motor, or water, or whatever other residual, or if you are below 150 degrees, below that, it's going to be difficult to convert that energy in something. And then we saw a variety of technologies such as Peltier cells, which can convert whatever temperature in the range of 15 degrees as a delta temperature. Okay, it's very low temperature, but it's very low power. But anyway, in the near future, perhaps developing new materials, it can be, you can extract more heat. And this is direct. Remember, you played with that. This is the direct conversion of thermal energy to electricity. And then we have ORC. What are the ORC cycles? The ORC cycles. To remember ORC cycles. Come on, guys. Organic Rankine cycles. Organic Rankine cycles, which in essence, we're depending on the fluid. We use isopentanol, we use butanol. If you compare the traditional Rankine cycle, you have the typical bell entropy like this. So you can reach up to 35–40% efficiency from the thermal energy to electricity. But if you move to an organic compound, it would be something more ugly, something like that. And then you get 11%, 12%. I'm talking about the Kalina, I'm talking about organic cycle, also Kalina cycle. In Kalina cycle, you have a mixture of ammonia. Okay. This is not Star Trek technology, as I mentioned earlier. Actually, we can review the documents. In Finland, in the municipality of Finland, all of you were in Finland, municipality in Finland, they have a waste management plant where they have organic material. This is converted into methane, and methane goes to a combustion machine to generate electricity, and the exhaust gas from there, from the combustion machine, goes to organic Rankine cycle. So they are introducing the technology. It's way too expensive. Even in our case, we tried this organic cycle using solar ponds. Solar ponds are big swimming pools where, in our case, we concentrate lithium. It's the one that we're going to study today. And then we can extract heat. 80 degrees Celsius, it's enough to convert this 80 degrees Celsius with a Kalina cycle into electricity. Actually, we did a project for San Pedro de Atacama. It's way too expensive, forget about it, it's way too expensive. But let's think in the future. We are preparing students for the future. Let's say in 10 years, perhaps it's going to be more efficient, but we did it. I want to incorporate this case too, because just to continue with that. And to finish this part, I want you guys, Eduardo, I want you guys to see how to convert the energy, thermal energy, into electricity. In order to do that, we will be working with HYSYS. HYSYS. There are two programs, HYSYS, yes, and HYSYS. HYSYS is a little bit easier for simple things. So you will start with when you put energy, thermal energy, whatever thing you do. So I need to write it down, but just to have the idea here, and then you will you evaluate different fluids. We can assign different fluids. Because the one that I want to do is step by step, because it's easy. You start with a heat source, and then that goes to a turbine, and then you will generate power here. You will see the kilowatt that you're generating. Then you need to remove the heat. You need to have a condenser, and then here you have a pump, isn't it? To put it back here. Okay. It's very simple, step by step, but you'll be using let's say, a high-tech software because it's for industrial applications. It's not software for. I mean, if you're playing with HIC, this is something like this in the world, but Aspen is something really, really, really complex. Okay. I just did it for water system to compare. So I ask you, for the group, having a step by step, and assign the different fluids. I'm not going in detail in the programming. We're going to have a special session because you need to choose the components. Then you need to choose the thermodynamics. Okay, and then you create the flow sheet. And then after you create the flow sheet, you simulate, and then you put the numbers here, and you will see, and we will compare. The number that I'm looking for is get this efficiency. I want you to compare different. Water will be 30% efficiency. If you use butanol, it's going to be something different. If you use isopentane, whatever, I don't care the molecule, but I want you to see that you can play with different temperatures. As a reference, we can use Ivania Novakovic's thesis that was referenced in the previous presentation. Okay? We are done with residual energy. Remember, another very important technology to move energy from one point to another point are the heat pipes. Heat pipes. So in the presentation that you already have for geothermal energy, we use heat pipes. Okay? Remember the heat pipes. The one that you have in your computers for cooling the computer, cooling internal fluid, you remember the heat pipes. In the project that we did with solar ponds, we want to see solar ponds now, since they have very, very high concentration of saline water, very viscous, accumulate heat, and then you can have 80 degrees Celsius, for example. It accumulates heats. And then to extract this heat from a very saline solution, the only way is using heat pipe, because a heat pipe, essentially, a heat pipe is a pipe like this one, nothing else, and internally has the liquid and transfer here. So for maintenance, you just remove the pipe, clean it, and put it back. Super easy. This is the advantage, okay? By the way, those heat pipes, and this is, I think, is in the Maria Jose Ulloa, who's working here now. The references are there. That those were invented in 60s in Israel, 60, in order to extract thermal energy for solar pumps. Okay, so we're done with residual energy. Now we're gonna move the topic. We will go to lithium. Not because we want to study lithium, just because we have saline solutions, and in this process we evaporate a lot. The idea there is how to make more sustainable the process. At the moment, it's evaporating the water. So they say that if it's saline water, it's not water. So by law, they're not using water. You know what I mean? In our regulations, this very high concentration brines, 200,000 microsiemen. In our regulation, this is not water. So we are not being unsustainable, you know. But we know it's not true because we are evaporating water. So in terms of law, in our regulation, they are not doing anything wrong. And then the companies who extract lithium, they have the green stamps. They are sustainable. But if we review, it's not like that. So I call it the presentation they just sent today morning, the dark side of electromobility. Not because I'm controversial, not because I'm creative. This is one news from Germany, Deutsche Welle. They call it like that. Sorry, I haven't downloaded. You already have it. So, okay, we are in the side not criticizing, we are not in the side complaining because environment, we are in the side when we have a problem, we see a problem, we tackle the problem with technology. So there is a problem, there is a concern from the community that the lithium technology has a dark side because during the process, in order to get lithium, you need to evaporate a lot of water, a lot, millions of liters of water per ton of lithium. And again, this is not illegal in Chile because this saline water is not water. It's not considered water source. It's not considered water. We cannot drink it. We cannot use it. So regulation says it's not water. Okay. So second page that you have there, this is the problem, the dark side of electromobility. So as engineers, as technology developers, so we need to develop something in order to improve the process, remove the water, and also collect it. So I'm about to show you a technology development. This is our role. You know what I'm trying to say? Not only say, I have one colleague right there, Professor Ortiz. They have projects saying, reverse osmosis is not good because it contaminates the sea when you discharge the saline water. Perhaps, but as a process engineer, what can I do to avoid that? You know what I mean? It's not the focus. It's not saying we want to study the impact of the ecosystem. Yeah, it's important, but we don't know if it's really impact according to me. No, but perhaps in 50 years. You know what I'm trying to say? Not only diagnosis, evaluating. This is not our role. Our role is to develop something to reduce these impacts. Okay. So this was exactly the same that I presented in the last conference in Las Vegas, which is not, it sounds very interesting, but it wasn't really good conference. So it's already connected there. So I want to show you two things. I want to show you how do you present in a broader audience, not technical audience. The whole thing that we've been seeing is very technical. Very technical. So now how to present the case in order to be engaged with the, here. I think already did it. Okay, things already connected, everything's set. So this is only for you guys, this is the dark side of electromobility. And now our really important task is a technology, water recovery by assisted evaporation in lithium extraction from solar pump. This is focused on lithium industry, but whatever, you can got some water. Whatever residual water that you have from reverse osmosis plant, from other operation, whatever dirty water that you have, we have developed a technology that allows you to extract the water, regardless the quality of the water, which this is a very important point to understand. And this was developed for lithium industry, so in the same operation, we also improve the crystallization process. So we will be studying evaporation. That means we will play with a psychrometry chart, humidity, air enthalpy, things that perhaps you already you don't know, but you will learn, because it's important to understand this heat transfer. Now we can explain the lucky bird. It's already here. So I add extra slide in order to go deeper in understanding the thermodynamics that you have when you mix water and air, so to understand the thermal balance. Okay. So again, this was for a broad audience. Some have another objective here. How do you introduce something which is very technical for? Actually, there was one lady from Ghana. I think I told you from Ghana. She works in more in policies in the government in order to assess the plastic impact and stuff like that. So people from different variety of areas. Okay, so the different countries, Sweden, Denmark. So I saw in the presentation different people from variety of countries. So I need to take care of them to say, okay, I'm coming from Chile. What are the context of mining in Chile? From the top, in order to understand what is the current situation. Okay, and then the lithium extraction. Why is important lithium for electromobility? Then solar evaporation zone, and then my main objective is the new technology. It's a technology that we developed here in order to recover water. Okay, so in short, to let the audience know well in advance some ideas. Say, oh, what this guy is talking about. So technology, hot air dry bubbles. Hot air dry bubbles. What is that? Hot air dry bubbles. Sounds crazy, so it caught your attention, isn't it? Okay. Conclusion: application of recovery water from brines. That's the main objective: recovering water from brines. So you at the very beginning know where you are going. This is completely different when you put topic, introduction, objective, methodology, results, conclusion. Don't do that, please. Don't do that. It's obvious. That template is for a philosophy, psychology, whatever activity you do. Please don't do that. So you must be clear that you have transmitting the clear messages in order to get the attention. Okay? Clear? This is Chile. Already are here. Very long country, wide country. Actually, is the longest country in the world. Those are the main materials that we produce: copper, iodine. Main producer of iodine in the world. Okay. The audience was one guy from Japan. The second one is Japan. Then you interact with the audience. Okay. Lithium. We are not good in lithium. Australia is going very fast. It's larger, but we have the largest deposit lithium in Bolivia and Argentina. It's going that, in my opinion, it will be Australia, Argentina, and then Chile. We are slow, very slow. But anyway, we have a lot of lithium. Then the funny thing, not only in metals, we also have very good one in salmon. We compete with Norway. We are the second in the world to go in salmon. Just to change the topic, okay. The mining activity is very intense, you know that. So this plot is very impressive. This is the north part of the mining operation. The largest copper mine, iodine, molybdenite. So seeing that, wow, Chile is the north part. It's a mining country, extremely mining country. Just to have an idea, just Escondida processed 300,000 tons per day. 300,000 tons per day. 300,000 tons per day. So a lot. Why lithium? Lithium is a buffer of energy. It's a, let's say, good battery, but not that good because after 5 years we need to recycle. So I don't think that we're going to continue with lithium batteries. We're going to do something different. Anyway, so this is the demand of energy to be storage. It's a lot of energy, so we need a lot of material. So, and that was a good idea at the beginning, reduce CO2 emission, replacing combustion engine machines with electrical cars. That was the main idea. Using wind turbines, solar energy, but we need to storage in some point. Okay. Impact demand strategic element. The most relevant is cobalt. Cobalt, it's really relevant. It's extracted only in mostly from Congo, and most of the companies are Chinese. 80% of the companies are Chinese. So it's an exploitation in a, let's say, in unhuman conditions for the people that live there. Waste generation after lifespan. We're talking about that. It's a good idea, but we need to think that we want to generate huge amount of battery. The same thing that is happening today with solar panels. Today we have a problem with solar panels. Today we have a problem with the wind turbines blades. My colleague down there, Henry Hansen, he's from Denmark. He worked with recycling wind turbine. And perhaps in the thesis topic there is some. Yes, there is one topic in recycling wind turbine. It's a problem. Okay. In our case, process extraction and efficiency. Water is evaporated irreversibly. But then again, say, because you have water cycle, it goes to the atmosphere, then come back. No, it's not true. It doesn't come back. All the water levels are going down. Okay, but it's debatable. But we're not going to talk about that. We just say it's debatable. Okay. So we'll be focusing on that. Of course, the batteries are used for storage. Those are the car, but it's important to understand that the amount of lithium that we have in the car is very little. How much? Nothing. So our president wants to build batteries in Chile because we have lithium. This is completely wrong, because you need to bring material from different countries, CO2. This is very stupid. We're talking about sustainable engineering. If we want to build something, we need to reduce transportation of the raw material. That's it. So please do not fabricate batteries. Understand? It's an important concept to understand. It's not only from the material, it's not recycling. The transportation is the most critical thing of the raw materials. Clear? Well, in our case, we have a great advantage. It's very good. God was very good with us. Long country, all the weathers. We don't need mining operation. We don't need to extract an ore. We don't need to process this ore. It's already in natural occurrence as a brine in a solution, which is good. The alternative, it can be from a mineral called, what is the mineral associated with lithium? Spodumene, which is the plant that perhaps you already know in Finland. Bertil Lamper, the guy who developed HIC, was in charge of developing the plant in Finland, starting from spodumene, meaning mining, extracting, crushing, leaching, process. But they are doing it because it's important for them. In our case, we have lithium in solution, 0.2%. This is a lot, by the way. And then, but it requires to be concentrated. So it's natural occurrence, we have lithium. Natural occurrence. Very good for us. High sun irradiation, a lot. It's the highest in the world for solar panels, all this stuff. Highest. So that helps to evaporate. Very low humidity. First concept for a psychometric chart. Very low humidity means the air has a lot of capacity to remove more water. To make it simple, when you take a shower and then you try to dry your hair in the bath, or you do not my case, if you do it inside the bathroom, it cannot be done because the air is saturated. It's very difficult. It's better to do it outside. But if you go outside, you feel cold because you're evaporating more water. But if you remain in the bathroom, it's not cold because everything is saturated. You do not evaporate water. Your body is not being heated. So when you have very low humidity, the gradient for mass transfer is very high. Understand? You cannot dry something with saturated air. Okay. So these two conditions, we're talking about 40% humidity, very low. Here we have about 70%. So let's say, to feel what it means, humidity and temperature. It's not the same being in San Pedro de Atacama with 35 degrees, going to swimming pool, you go outside the swim, it's really cold because it evaporates really fast. But if you are in Rio de Janeiro, 90% humidity, okay? Same thing, same condition, you feel extremely hot, bloody hot. Philippines, same, bloody hot. Because with the humidity, you do not evaporate. We control the temperature by evaporation, water. Understand? Same temperature, but humidity makes the thermal sensation completely different. Okay? So we have very good conditions to evaporate. So those pans evaporate for 12 months, 15 months, and the capex, the investment to build this, I'm talking about 500,000 square meters, 500,000, sorry, yes, 500,000 square meters. One, big. So, capex for 0.2% lithium is 30%. Let's say in a project, it's a lot of capex, but in the case of Argentina, it can be 50%. Because as you reduce the concentration in the original, you need more ponds. So having 50% investment, and you have a lot of losses because you have a carpet, kind of carpet, HDPE. When you remove the salt, you cut it and you lose a lot of solution. Okay. So it's good for the condition, it's cheap operating condition, but it's not that cheap in terms of. And this is the view from San Pedro de Atacama. So there are two plants there. This is really big, really big. That's how it looks like from San Pedro de Atacama. Yes, I think you can go there. If you click there, you go to Google Map and you will see, and you can really. Actually, you can assess just measuring pixel by pixel here. The evaporation rate there. But let's say here in a swimming pool, the evaporation rate. An evaporation rate is, how much is an evaporation rate typically for water? See there? You want to evaluate how much water are you losing? Evaporation rate. Number, engineers. 10 liters square meter daily. It's a standard evaporation rate. If I have this one with water, I can determine how fast it's evaporating, just knowing the dimension. It's extremely dependent on temperature because the vapor pressure depends exponentially with temperature. Very important to understand that. And if I have saline solution, the vapor pressure will drop a lot. If I have only water, the still water, it will evaporate this rate. But if I put a lot of salt here, it will be dropping because the vapor pressure drops when you have ions, okay? This is water. In a brine, you can have 6 to 8 brine, okay? 6 to 8. Because of the effect of salt in the vapor pressure, okay? It's effect of salt. This is called thermodynamics. Colligative properties. The same thing, colligative property. The same thing, to avoid freezing the fuel in your cars, what do you add? Ethylene glycol. Then you reduce the freezing point. You change the eutectic point. Okay? In this case, you reduce vapor pressure. Anyway, it evaporates a lot. This is the diagram. You start with saline solution, 0.2% lithium. 12, 18 months evaporating, and then you transfer solution to a different point and remove salts. You are precipitating different salts. You end up with 6% lithium. This is the high mountains in San Pedro. And since there is not electricity facility there when this was developed, all the plants are near the coast. And the lithium solution is transported by trucks, 300 kilometers, being processed in order to produce lithium carbonate and lithium hydroxide. Lithium carbonate is the most common. There are two big companies, Albemarle and SQM, largest producer. So this is from Albemarle, an American company. So you have different ponds, evaporation, and you produce different components. You're removing. But in this path, you are also precipitating lithium and also entrail lithium. You have solution with crystal. They claim that they are putting all the water back, but it's not true. You are evaporating a lot. When you remove that, this is wet. This whatever crystal you have is wet, and also to make it simple, with the data that they have, the efficiency is 50%. It means the lithium that you extract, evaporate. Efficiency is 50%. This is very bad, but nobody cares, because in our case, the owner of the mineral is Chile, the country. And they pay, for production of lithium, they pay royalty for production, not for the efficiency. This is really stupid. Okay? So not important for me. Again, this data is from the web page from Albemarle. I know it's 30% efficiency for different balance. 30%. Okay? Again, not criticizing. As a process engineer, let's think in alternative technologies. Okay? This is a calculation, with Google Map, to make it short. This is evaporation rate. When we talk about this area, so we're evaporating 6 cubic meter per second. This is equivalent to, a big city. The consumption, 200,000 people, 1 cubic meter. So this is 1.2 million people drinking water. Okay? You don't know that much. You can do it. Check it, swimming pool. Okay, 3 liters per minute. This is too costly. Don't care. It will be again 3 cubic meters per second. It's a lot of water. Okay? That's what we call it. This is for fun, because I've been talking too much. The audience, and you wake up the audience. The right time. This is called the dark side of electromobility, because you remove 2.2 million liters per ton of lithium. I didn't do the calculation, but it's in this Euronews. You can go there and you will see. Perhaps they are mistaken. I don't care, but the perception of the community, it's extracting lithium is bad. And also we need to take care of that. That is the message. Okay? Understand? The sequence of ideas. So how is the production? Not only the water, it's a little bit more complex than that. So this is the evaporation pumps we are moving. And then it's transported by truck. It looks very short, but those are 300 kilometers. Imagine the CO2 footprint. Okay. You process, and then you generate again another solution. This solution is more concentrated than the original one. You can have even 900 grams of ions per liter. You will not believe me. Actually, one professor from Israel didn't believe me. So to show you, it's like a honey. And since the concentration is very high, the vapor pressure is very low, and if you want to evaporate, to remove this water, in Antofagasta, which is by the sea, 1 liter per square meter they have. it will not evaporate. They don't have ponds enough in order to process. What they do, put it back in a truck again and come back to the plant. That is what's happening today in our process. Okay. Determining the evaporation rate is really, really complex. Actually, the company have a model that is not that good. Last year, we developed a different model based on environment in order to predict environmental meteorological data. Those are the days, 250 days, day by day. So the blue dots is the actual measurement, and the red dot is our model. You see, it's very cool. Nobody has done it before. Okay. To determine the evaporation rate, because you want to forecast, because you have different based on climatological. Okay, so we need to know for real what is the evaporation rate. Okay, so some cases it's very high for radiation and a lot of wind. When you have wind, it increases a lot. That's blowing. Okay, so you have very high. We talk about 6. Okay, but it can be even higher, 12 liters because you have wind. When we talk about 10, it's in a steady state condition, no wind. You understand? It's different. Okay, otherwise you're removing a lot of air. Okay. So we did that modeling with neural network just as a pretext in order to train you in a tool. We will come back to these numbers. You will play in MATLAB to model that with MATLAB. It's super easy and you can model whatever thing that. And since we are in the context of evaporation, we will share the data because we have good data. This is another thing. These companies has a lot of spreadsheet, but they are not connected together. The only thing that we did with MATLAB, we put all together in a big database, and we were able to model the evaporation rate. So last year. And actually, this student, this is Ivania Fernandez. She's working already in SQL. He was hired. He's working already in SQL. So, not part of this class. I think in an assignment as a pretext to play with neural network in MATLAB. It's another little assignment pretext to learn how to use it. Those are imagine that. So this is the comparison, real data, different combinations. At the end, we just need we just need some 7 layers, very little information. The average temperature, minimum, max, and humidity. We can predict because temperature can be predicted easily for forecast, so you can see how much are you going to evaporate. This is in order to determine what is the right time to stop the evaporation process. Okay, understand? So we need to have modeling tools. Okay, this was parenthesis. Coming back to lithium brine, this is already in Antofagasta, so they have these ponds in order to rid off of the remaining solution. But since they are near the coast, the evaporation rate is very low, 1 liter per square meter per day. And given this high concentration, then you have less vapor pressure, and then returns back to the altiplano, 300 kilometers back. So in both cases, desperately, we need something to extract water, either to concentrate, to remove the water and reduce the volume of the solution. In this case, this is a waste residual solution. In other case, we need something. We cannot use membrane. It's too high the concentration. And also, we want to recover the water. We evaporate, we want to separate, we want to recover the water. Okay, it's a very complex problem because this solution is very, very bad. Of course, evaporation ponds is not a good way to process lithium. This is completely wrong from the beginning. I've already have the installation. There are alternatives. In evaporation point, actually 30%. This is the efficiency extraction. But we can have direct extraction. And this thing already exists. This is a plant in Argentina with a French company, Eramet. They develop a process for direct extraction based on adsorption. Also, you can study with membranes, but again, working with solution membrane. The technology is going in that direction, not evaporation ponds. But we already have it. Okay? Those are the alternatives. Ionic exchange. Solvent extraction has been done for 30 years. Myself, I did it with Professor Rebeco in 90s. In 1990, as a student, I did experiment with solvent extraction, using solvent extraction, using an extractant called TOPO, trioxyl phosphide oxide. I did it as a student, solvent extraction for lithium. But the only problem is some solvent can come back to the water body. So it works very efficiently. Membranes too, like reverse osmosis membrane, but the one that has been developed by Eramet is ionic exchange. The plant starts on. I think you attended to the conference with my colleague from Eramet. Did you? Okay. So this is the top technology today in lithium extraction. Okay. But let's come back to this problem. Regardless lithium or not, we still have the problem with what can we do with dirty solutions or nasty solutions with either a lot of ions. What can we do in order to reduce the volume, because we cannot process because we don't have ponds. Reduce the volume and recover water. So this is a big problem. We see it in the case of lithium, we see it as an opportunity. Very low evaporation rate, a long time. It's 12 to 18 months. Very high the capex, 30-50% capex for the technology. Recover, we're being generous. It's not 50, it's less than 50. Okay. So this is an opportunity. What are alternatives? Okay, reverse osmosis is very good for seawater. Very good. No way. It's the top technology. You can get potable water with today. Reverse osmosis is the top one. Paula will be talking about that. Already been talking about that. Today you can have $1. This is an important number in your head. $1 per cubic meter of potable water. If you consider energy cost 60 US megawatt hour. So if we have less cost in energy, cheaper. And this cost includes capex and opex. This is the current cost today. Energy consumption to produce from seawater with 50% recovery. 50%. This is the actual technology. We cannot do more. So it means start with 35 grams per liter of salt, residual water 70, double grams per liter, and the consumption is 3.2 kilowatt hour per cubic meter. This is our current technology. Very top. Okay? So the water problem has been solved. We only need energy. From seawater, but we cannot use when we have more than 70 grams per liter. Saturated, it's called membrane polarization. Because the ionic charge is too high, then you cannot work with the current technology. This is the limit. We have how much we have? We have 700, 500. The brine has 500, so no way to work with reverse osmosis. And then thermal evaporation, yes, very good. but you need thermal energy, a lot of thermal energy. Remember that to evaporate water, the heat evaporation, I mean, just to have a number in your head, I know it depends on the pressure, but to evaporate water, you need, correct me if I'm wrong, Eduarda, a kilojoule of energy per kilogram of water. Can you shake? I'm talking about lambda water. Can you shake it? Can you shake it? It's a lot of energy. Can you check the heat evaporation of water? Lambda. Check the number. It's extremely dependent on temperature, by the way. Remember the bell? It's extremely dependent. What's the number? Lambda? Water lambda? It's the number, right number, okay? So we need a lot of energy. It can be done. So if you have free energy, like Saudi Arabia, they have plants. You will see that with Paula. But besides that, they are also moving to reverse osmosis. They have free thermal energy. For them, the oil is cheap, nothing. And now they are replacing thermal plants to produce water with oil. Okay, but in general, it's expensive. And more importantly, it's not sustainable because you need to burn fuels. Understand? Ionic exchange, solvent extraction. The economical cost is limited to that. If you are above 10 millisiemens, seawater is 45 millisiemens. Seawater is 45 millisiemens per centimeter, the conductivity. Okay? If you are below 10 millisiemens, it's more cost effective having ionic exchange solvent extraction. If you are over that, you need to go to reverse osmosis, but reverse osmosis is limited to, let's say, 80 millisiemens of conductivity. Okay? Then electrodialysis, very low concentration. It's forward osmosis, it can work. For forward osmosis, it can work because actually it's called forward osmosis, but it's not true, it's a commercial name. It's really only osmosis. Because you have the same membrane, but you put in contact very high concentration with brine, with water and ammonia. In this phase, you have 70,000 ppm of ions, and here you have 200,000 with water and ammonia. And then you have osmosis. Water will go to the higher concentration easily. Okay? But membranes get scale. Whatever thing you put, interfaces is going to be scale. So we need to invent something that has some membranes. You know what I mean? In dirty situation, we need to avoid scaling. Okay. So it's not suitable for dirty when you have clays, when you have solids, high concentration. None of them is suitable for that. Okay. So we end up with this technology. Actually, it's 4 years. We introduce air bubbles, but these air bubbles are dry and also hot. Why do we need it hot? Because as you increase the temperature of the air has more capacity to retain water. If you have this air here, you can have 30 grams of water per kilogram of air. A kilogram of air is 1 cubic meter. So something like this, you can put only 30 grams. But you have the same air at 80 degrees Celsius, you can have 700 grams. Why is that? Because that depends on the vapor pressure, and the vapor pressure is exponential with the temperature. Again, so in this condition, we call it stoichiometric charge. We will go to that. When you have 1 cubic meter of air, you can have only 30 grams. Do you remember stoichiometric charge? We will see. 30 grams. But when you have 80 degrees, I don't know the number exactly, but you can have 700, 600 grams. So you have a lot of water. So we introduce these air bubbles that you already know, in flotation, air bubbles, and then the air bubble, since it's dry, it has a water layer around, it will evaporate internally. And then we remove the water. And then since you have air, the air by natural buoyancy will float and take your water. And then you condense this hot air. So in order to understand that, we need to play with the psychometric chart. You can download now in your cell phones psychometric chart application. Be careful, there is another one for psychologists. This is not the one that we're using. Okay. Whatever I don't really care which one. All of them do the same thing. Okay. See?
Is that bubble injected at the bottom of the pond? It doesn't make any turbulence.
No, you will see. You will see. It's a new device. Yes, but yes, you could inject it in the pond directly too, but they are too big, 50 meters. Okay, you can inject it too, and this water will increase the evaporation rate, but you cannot recover the water. But it will accelerate. Actually, the number is you increase 80. In the experiment we can reach 80 liters per square meter, so 10 times. Okay. But the important thing to understand is psychometric chart. If you don't have it, I think we want to use it. Here you have the temperature, and then you have the humidity, the one that I told you, 30 grams per kilogram of air, dry air. And then you have the enthalpy, the energy, and then you have the humidity. You have different humidity. This line, and you have 100% humidity. We will see that. I have it. I have links to play with the numbers and to play with the psychometric chart. I just you want to understand that we're using a special capability of the air to retain water, and we're using our experience and knowledge in generating bubbles. I mean, we are specialized in bubbles, everything regarding bubbles. Okay. So this is the conceptual design of the. This is the air bubble. We already know. We understand. We understand very well that it is a liquid layer. We've been playing in the other course in the process design. That depends on the frother. Remember that. So this is a water layer. We're studying a lot. More importantly, when you have saline water, it will help to have smaller bubble size. And we want to have smaller bubble size in order to have more area to transfer and also to move slowly in order to get saturated. By the way, saturation takes 2 seconds. It's extremely fast. We measure it different. By the way, I was talking with a student, it's fascinating. He's in Austria now. Yeah, no, Germany. The guy who worked with that at the beginning, I was telling him, we're talking about these hot air bubbles. So it evaporates really, really fast. So that is the conceptual design. You put fresh brine here. Bubble, what is the air bubble here? Is one missing around here. You inject hot air bubbles, and then the air with the water will come out with saturated water. Careful, but when you burst the bubble, you will generate micro droplets of solution. Very tiny droplets. And those will be carried, so it's not pure water. If you don't have this droplet, you can have a demister to reduce that, something that collides the droplet, but you have some. Let's say in cooling towers, when we use evaporation to cool down the water, cooling towers, the drift, this is drift, how many droplets of water are you losing? It's 0.02% of the total amount of water that you're circulating. So it's very little, but this very little, very high concentration, we put some ions in the solution, okay? But anyway, it will be very, very good quality water. And then, since you evaporate, it's an energy balance, some of the brine will be cooled down a little bit. Because when this evaporates, this bubble is going to be cold. And we tested that experimentally. The bubble, the surface of the bubble will cold and will cool down the solution. And this is good because allows you to precipitate salts. In the same agreement, you recover salts. So we're removing water, concentrating, or we remove water, also precipitating salt. This is the conceptual design. Now, if we put more stuff at the end, it will be something like that. Then you have the fresh water, the fresh brine. Let's say I'm just inventing a number, 20, whatever number here. You inject hot, dry, micro air bubble. They are micro because you have saline solution. So it works as a surfactant. You already know that. Okay. Evaporate, you end up, you will lose some of the heat because you are transferring heat here. You end up with hot air, saturated 98, 95, 98, because we measured that, 98% humidity, saturated. So you have a stream with very high enthalpy. We were playing around with Eduardo and a balance with enthalpy to put the numbers. It's not the same having dry air in terms of energy, or having 80 degrees hot air, or having 80 degree hot air with 90% humidity. It's 90% humidity has a lot of energy, enthalpy accumulated, because this lambda. So condensing that is super easy. If you have nothing, just condense it to the atmosphere, because very high temperature, 80 degrees, it will cool down, but you can recover this energy. So you are listen up, we are generating energy here for phase change, just condensing. And then we don't want to lose this heat here. You can remove some water. You don't need really to remove some water in an absorbent. And then you need to heat. Here is the money. 2 degrees, 4 degrees, 2 degrees, 4 degrees, no more. Okay? And then go to the blower, come back here. Here's the money too. We need to have a gas disperser that has not a lot of pressure drop. If you have a porous spargel, you need 60 psi. But if you have very low, very shallow one, I mean 1 meter, 1.5 meter height, and very high concentration of saline water, the salinity will help you to have very tiny bubbles. So you can work with a very high porosity spargel, so you have less pressure drop. You follow the sequence, okay? Since you have surfactant solution, you don't need to have a small pore size. You can have a low pressure drop spargel. You know what I mean? Okay, and again, I made up this number only for the conference, because I mean, we don't need to give too much technical information, but you pull down the solution which you're evaporating. So the energy balance must fulfill, okay? So this is the energy, you make the summation here, this is the energy that you pull down. You will be playing with that in this energy balance. It's not that complex, because if you know the conditions here, humidity and temperature, you have the enthalpy directly using the psychometric chart. Enthalpy means how many kilojoules of energy you have per kilogram of dry air. Working with air is a lot easier, so the psychometry chart is really, really good. Okay, super easy.
In the first stage, you mentioned that about 2 to 3 degrees that we can recover.
I mean, we lose some temperature here, and here when we condense, we only change phase, which we just remove the water. We don't want to change the temperature. It can be reduced to the temperature. So here, we need to increase in order to have this condition, because we lose some thermal energy of the air itself. You know what I mean? Of the air itself. So we need to heat up a little bit. So again, we have you will see a lab scale, and now we need to scale up that. Actually, for this company, they want to have the exclusive license for this. This technology, by the way, is patent already. It's a patent in Argentina and Chile. It's already patented. So you're seeing a patent technology here. Okay, I will not go in that. This is the psychometric chart. You can go to this book, Chemical Engineering, and also all these web pages. When you will see, understand, I want you to play to see what is the energy, what is the humidity, to understand psychometric chart. Okay, so it's important It's an assignment here, you to study in order to understand the rest of the assignment. Okay? You already know that, this is mass transfer. Okay? But you need to play with this different demonstration to understand what is the value of energy. The most important thing, you need to know only two things of the air. One of them is the temperature, the other one is humidity, and then you have all the data, or something that we call wet bulb temperature. Wet bulb temperature. Okay, got it with that? You need to study psychometric charge, how to get the numbers. Again, more examples, how to play with that. This is online, you can play here. You can download your application for psychometric charge. Just to see, this is the humidity line, just to understand when what part of the curve. Okay? Now the lucky bird. Okay, the lucky bird. I want to skip the lucky bird because it's the example that I use in chemical engineering class to explain wet bulb temperature, and you saw that yesterday. Did you figure out how it works?
Yeah.
Okay. So you explain your classmates, but give some time to them to understand, to figure out how it works, because it's a very good mental exercise. Also, we're playing with a thermographic camera to see the temperature difference. So the thing is, with very little temperature, you can generate a lot of difference in terms of vapor pressure. Well, coming back to the technology, there are two things. The first patent is the concept of injecting air in order to evaporate water internally. This is the patent. Yes.
I want to ask if this backup technology can be applicable to after you call
I'm sorry, I didn't quite follow.
this backup power technology, is it applicable to the other brine solution you generate?
Yes. Both of them, receiver and altiplano. But it's a device. We're not using, we're replacing the ponds, no ponds. We are replacing ponds. And actually the one that I want to show you is not the real one, it's not a chamber. It's a column with a loop. It moves alone because you change density. But I cannot show that because this is our technology. Okay? But this is the concept. Okay? Let me continue. So there's two things. This is the conceptual design, and also there is another pattern regarding the gas injector. You already saw that, you already saw the video. To introduce the air in order to control bubble size. We have a shear stress here. Okay, this is the other device when you inject air and you put some solution going through in order to produce some shear stress and control the bubbles. Okay? It's very likely in very saline solution we will not use it because it already has a lot of salt and works as a surfactant. Okay? But in the case it's not that high, we can use this because you saw in the movie, you saw in the video, remember? Like smoke, very small bubble size. Okay? So that's the thing that we did. We simulate the absorption processing aspect. This is a different model. We don't have anything, but we did we use Aspen Hysis to simulate the model. And then this is the actual column that we use to dry the air. We dry the air here, the experiment. And this is the evaporation tank. This is the one that is downstairs. This is the one that we use, that we design. By the way, this guy also is working, this Elias. Elias also working in research and development in SQM now. He was hired before having the degree, by the way. Because today it's very difficult for men. Getting jobs in, not difficult, but it's more competitive because the women have more chance to be hired by definition. Really, it's happening. But this guy was hired very quick. He worked with that. Okay. So this is the device, the chamber. The one that is being developed for this purpose are columns, two columns. Inject air, and then you have gas holder here, no gas holder, and start recirculating. I have a video, but I cannot show you in the conference but I will show to you. Actually, I have it in the lab. You will see. It's one of the thesis topic, by the way. This is one of the thesis topic. I think number 3 or 4. We put 5 topics. This is there. So what we achieve with this, gas velocity, that, the temperature we achieve. Imagine that 100 experimentally, 100 liters per square meter per hour per day. So increase 10 times the evaporation rate, but also we recover the water. Not only evaporation, it means a quicker process with water recovery and precipitation in the same vessel. You don't need to have this pond because you need to remove all the water in the pond, put a machine to remove all the salts. You know what? Then it's deposited there. It can be continuous. So this is the great advantage. This is the industrial prototype again. That was we were developing, but we came up with a different idea. That was thinking to work as a pilot in the plant, but now it's completely different. It's a column reactor. It's easy to build. So where can it be used? Extended application, whatever solution you have. With solid, it's not important because you're introducing air. Air is going to be saturated in water. No way that the air is going to get solid. No way, because you are evaporating. The bubble burst. You know what I mean? And you can transport some droplets. Okay. This is very important for reverse osmosis. Reverse osmosis has been, there are community complaints because you are discharging saline water in the sea, you are discharging water, okay? Because you reject 50% of the water is being rejected. So community say, no, contamination, blah, blah, blah. Okay, we have something to extract more water now, okay? So, in conclusion, what about time? So we have developed a brine concentration technology with water recovery and energy efficiency, because we use the condensing phase only. Production of fresh water. We have thermal energy. Again, here, we can heat something else around the plant. We have thermal energy to be used. Easy to use, 80 degrees in terms of heat exchanger is a lot of energy. We can heat. So the technology supplies fresh water, thermal energy, and precipitated salts, because you concentrate and cool down the solution. We didn't design that. This is consequence of an idea. The idea was what happened if we put dry air bubbles. And then at the beginning, we did that. If you review Elias' thesis, we hot the solution. Why we need to hot the solution? It's too much energy. Why don't we hot air? And then we start studying. If it evaporates, cool down the solution. So we didn't invent all the things. I'm trying to say we're not genius. Those are consequences of the making the balance. The right idea was using dry air bubbles. And the concept of internal evaporation. Okay? Interfacial gas liquids. This number comes from 6 Ag P32 1 minus Ag. So as a reactor, since we have very small bubble size, not because we designed that, because there's high salinity, it works as a surfactant. As an accident, we have very small bubbles. Good for us, very high surface area. Interfacial area. For mass transfer. Okay? And residence time, I put 30 seconds for the audience only, but we need 2 seconds. We need 2 seconds to evaporate the internal evaporation. Applicable to any saline waste solution to concentrate with water recovery. We can concentrate something to reduce volume, but with water recovery. Okay? And that's it. Any question?
So this technology couldn't be applied in the present only to issue between.
It is. We tried with the. Okay, I want to close the recording. Okay. This is something now is negotiating the technology transfer and licensing. But I need to stop here the. It is not the thesis list. Now remember, it's not Eramet. It's not in the thesis. But it can be that thesis too. By the way, it's not. I didn't put it.